Hello everyone. In this project, the goal was to develop a classifier that predicts low-end defaults that maximizing the F1 score and ensuring the model is well fitted. To achieve this, I performed exploratory data analysis, extensive feature engineering, trained multiple machine learning models, applied hyperparameter optimization, and built ensemble models. In this video, I will explain how I improved the performance of my classifier, how I assessed and improved the model fit, and what I would do with more time and resources. To improve the model performance, I started with feature engineering. I expanded the original features into a richer set of around 45 variables. This includes ratio features such as debt to income, iteration features combining credit score with interest rate and loan percentage, employment to age ratios, and credit history based measures. I also created risk flags to capture high risk borrower behavior. For example, high interest rate or low credit scores. In addition, I applied log transformation to reduce skew and created polynomial term and credit score buckets to capture nonlinear relationships. These steps allows the models to better represent borrower risk patterns and improve the predictive quality. Next, I trained and compared several different models including random forest, XGBoost, LightGBM, a neural network using MLP, and stacking ensembles. The boosting models performed the best individually because they capture complex nonlinear relationships and interaction effectively. LightGBM and XGBoost achieved the highest single model F1 scores, while Random Forest provides strong interpretability and stability. The neural network showed competitive performance but required more tuning. I then combined XGBoost and LightBGM using a weight ensemble which produced the best validation F1 score, demonstrating that combining complementary models can reduce error and improve robustness. Here is some results graph run by our code. And another key challenge was class imbalance. Since non-default case significantly outnumbered default cases, instead of using oversampling techniques like SMOTE, which sometimes reduce the accuracy, I used the native class weighting approach. Specifically, XGBoost used scale post weight and LightBGM used the balanced class weight. This allows the models to pay more attention to minority default cases without introducing synthetic noise. I also optimized the decision threshold rather than using the default volume of 0.5. Because the evaluation matrix is F1, turning the threshold helps balance precision and correlate to additional performance gains. I also applied the hyperparameter tuning using Optuna. I searched across the parameters such as tree depth, learning rate, subsampling ratios, regularization strengths, and class weights. Early stopping was used to prevent overfitting and improve training efficiency. After tuning, Both boosting models showed clear improvements in F1 score compared to baseline models. This confirmed that careful optimization plays an important role in achieving strong performance. To access and improve model fit, I use a validation strategy that includes a stratified train validation split to preserve class distribution and cross-validation inside stacking models. This helped ensure that performance estimates were stable and not dependent on a single split. I then generated learning curves to evaluate whether the model were overfitting or underfitting. The learning curve indicates that the random forest showed some overfitting with training performance significantly higher than validation performance, while boosting models demonstrate better generalization based on this. I prioritize boosting the ensemble approaches. Here is a running result for different models. And this is the learning curves of random forest learning curve and XGBoost learning curve. And I also analyze the confusion metrics to understand prediction trade-offs. The best model showed very strong performance on non-default cases and good but slightly lower recall on default cases. From a business perspective, false negatives are more costly because approving a loan that later defaults creates financial risk. Therefore, I adjusted the decision threshold to increase recall for default predictions while maintaining reasonable precision. I further I've evaluated the model behavior using precision recall and ROC curves. These curves showed that the ensemble maintained strong precision even at higher recall levels, suggesting the model is suitable for risk management scenarios where identifying risky borrowers is critical. If I had more time and resources, there are several improvements I would explore. First, I would incorporate external data such as macroeconomic indicators, interest rate trends, or credit bureau information, which often improves the credit risk models. Second, I would experiment with additional algorithms such as XGBoost, advanced tabular deep learning models, or automated machine learning pipelines to further optimize the performance. Third, I will design a production monitoring strategy. This would include the tracking F1 score and default rates over time, detecting data drifts in features like income or credit score distribution, and retraining the model when performance declines. Monitoring is essential because borrower behavior and economic conditions change over time. In summary, feature engineering is the most important factor in improving performance, boosting models, delivered the strongest individual result, and ensemble methods achieve the highest overall F1 score. Learning curves, confusion metrics, and sharehold optimization helped access the model fit and align the classifier with real business objectives. With additional data and production monitoring, the model could be further improved and deployed in a real lending environment. Thank you for watching. Here is some actual result for our code. which generate by our model. Yep. Thank you.